Okay, so now today we're going to look at the normal distribution. So in the last video or last section you would have gone over a fairly simple section talking about continuous probability distributions, and that's what the normal distribution is. It's designed as a continuous probability distribution, or what we call a probability density function. It's a function because there's no holes in it, and it's continuous function. And so we call it a continuous probability distribution. There were a couple of key learnings that came from that. One key one that came from that, maybe I'll just take a sketch from the last one. Oops, previous one. One key learning that came from that is if we want to know the probability of anything, what we needed to do was to calculate the area under the curve. Okay, so we would define a range. Okay, so here's an example of a probability function that exists. It's a uniform probability function. And then what we would do is we would find the area under the curve. So the area under the curve, for example, I've drawn it down here. I take this exact same function. Okay, the probability is here, and then this is the random variable x. It's a continuous variable, mass or something. In this case, it's mass. And so the range that I want to know the probability of is between 100 and 400. So in this case, what I do is I ascribe what particular regions are created by that, and it's this pink area I need to figure out. So my probability between 100 grams and 400 grams is equal to the area, which in this case is the length times width. It's a simple function, so as a result, the area is just the length times the width. And you would have seen that with question number 6 from your homework as well. So it's a really good opportunity for you to understand that really the area under the curve is the probability, because we need that idea to go through what we're going through here, okay? Now this is beautiful for functions like this, but you may get to functions that look like this, that are curved, or have two curves, or even sort of a decreasing sort of curve here. We don't have an easy way to calculate the area. And so the way that you can calculate the area is, you know, the equation for that function, and what you can do is you can integrate it over the area associated with that value. When you do an integration, which is a calculus measure, it's like an antiderivative. Instead of doing a derivative, you do an antiderivative, for those of you guys who understand calculus. And then what you do is you substitute in some values and you look for the range between the two of them. And when you do that antiderivative, that gives you the area under the curve. So it's a very complicated thing to do. We certainly are not going to be able to calculate it for anything other than a uniform relationship, okay? And so this is the curve that we're going to focus on, all right? So now we can actually get to, the content that we were actually going to get to, which is the normal distribution. And I already talked about the normal distribution, a little bit about it, but here I'm going to go through it in more detail. So the normal distribution of the normal curve is a probability density function. You may have seen this in grade 11U biology. If you did evolution studies, and remember when you did evolution studies, this curve was let's say this is, I don't know, the height of a plant or something like that, and you would find out that there's a lot of people that are pretty much average height. Okay, so there's a high probability of finding a plant that's average height, or the largest percentage of plants is average height. And then there's some that are really short and some that are really tall. And then, you know, there's less that are sort of short and less that are sort of tall. So it creates this distribution. And this distribution is very common, seen all over the place. So it's really good, of course, for us to understand this distribution, because this is the way that a distribution generally tends to work out. Now, for those of us who are doing genetics, you can marry evolution and genetics together by understanding that this is for what's called a polygenic trait, which means the traits are controlled by many genes and many factors. And as a result, there's so many subtle forms of the gene. It's not like, you know, tall and short like it was for Mendel's pea plants. You can have tall and medium and a little bit short and not short and so on and so forth until you get all the way up to, and you meander around a central value. And so this is a really important idea because it shows us two things. Now, the scale for this axis is one of two things. For our purposes, probability is a really key feature, or it's a relative frequency. And that's an important idea to have for all that. So that when you get an answer, the area under the curve, it gives you two things. One answer gives you the probability of finding something within that range, and we'll be doing examples like this. And another will be the number of individuals in that population, or the percentage of individuals in that population that fall within that range as well. So whether it's a probability or a percent, as a percent likelihood, or whether it's a relative frequency, the percent of the total population that actually fall within that range, it's the same answer. Okay, so we'll be getting them interchangeable. And that, of course, makes it a very, very, very useful statistic. And really what it does is it takes what we're finishing off with, probability distributions, and bring it all the way full circle back to our single variable stats, because this is a single variable stat. Okay, so first things first, in your notes, I apologize, whether it's the version of Excel or not, the sigmas and the mu's have been replaced. So there's a lot of features that are going to be really important. But anyway, let's talk about a few of these characteristics. One, it's a distribution that is symmetrically distributed. Okay, symmetrical. In other words, this side of the curve is exactly the same as that side of the curve. Okay, perfect symmetry. Okay, the mode equals the mean. This is the mean, mu, but it's also the mode. Mode, remember, of course, is the most frequent value or the most probable value that can exist in that population of data or population of individuals. It's bell-shaped because if you take the side of a bell and you slice it in a what do they call it, a sagittal section, then you'll see that it's, of course, bell-shaped. It looks like a bell. And then unimodal, there's only one mode. Okay. The standard deviation is going to be an important characteristic to measure it, and the mean is going to be an important characteristic to measure it. For the normal distribution, what's called a Poisson distribution, the proper normal distribution, it has a few key features. One, its mean is 0. Okay, so the function that we get all the information from and all the calculations from, its mean is 0 and its standard deviation is 1. Okay, now you may say to yourself, well, that's stupid, because when I'm dealing with heights, my mean height could be 150 centimeters and my standard deviation could be 5 or something. Or if it's, I don't know, the mass of a chihuahua, then, the standard deviation is, or the average is, I don't know, 8 pounds plus or minus a pound, if that's a standard deviation. And so you're like, well, how can I use this to make it like this? Well, we're going to do a calculation. And that calculation takes your data, whatever it is, whether you're talking about the mass of an elephant or the mass of a bag of M&Ms, or the height of a redwood tree, or the height of a beetle. Doesn't make a difference. Whatever value you use, as long as it's continuous, then you can use this function. All you say is everything looks like this, and so what we do is we transform our data into this function. And once we transform into this function, then we can go and do all the stats for it, because we know lots about this one, where the mean is 0 and the standard deviation is 1. One thing that we do know, according to probabilities, is this, and this is a really key feature. Okay, if I go, this is my mean, if I go 1 below or 1 above, 1 standard deviation below or 1 standard deviation above, the area in this curve right here, okay, or the probability of being plus or minus 1 standard deviation is 68.27%, or about 68%, okay, which is a pretty cool, interesting idea. Okay, it's known that distribution is the way that it is. So it follows this curve and it follows this pattern. You can use this to emulate it. And so you take your data, and if it looks like this and it's distributed like this, then you can go ahead and plug it into this and then go for it. Okay, another interesting feature is if you go from 2 above or 2 below, so let's say the Chihuahua average mass is 8 pounds, standard deviation is 1, this would be 10 pounds, right? This would be 9. This would be 8, because that's below the mean. And then this would be 11 and 12. So between 8 and 12, the probability of finding a Chihuahua my mean was 8. 7 and 6, sorry. And this would be 9 and 10. So if my mean was 8 pounds, plus or minus 1 pound for a standard deviation, plus or minus 2 pounds, okay, or 2 standard deviations between 6 and 10 pounds, is going to be this area under the curve, and that area is associated with a percentage or probability of 95%. Now, this is a very, very, very important value. It's what's called a 95%. It's what establishes what's called a 95% confidence intervals. So when you go to university, you're going to go through that, and that's going to be your sort of testing feature to look for deviations or differences compared to what would be accepted. Okay, so the 95% confidence interval is something that you're going to see. Okay, so keep that idea in mind. So again, but plus or minus 1 standard deviation, 68%. Plus or minus 2 standard deviations, 95%. Plus or minus 3 standard deviations, 99.73%, which means basically everything that follows this shape is going to be either well, if this is 8 pounds, it's going to be between, every Chihuahua in the world is going to be between 11 and 8 minus 3, 5, between 11 and 5 pounds, which is probably reasonable for an adult Chihuahua, right? But you could maybe have the unusual one who's a little bit outside. That literally defines what is normal and not normal. This is a mathematical definition of normalcy. If you follow the normal curve and you're plus or minus 2 standard deviations above or below the mean, you are considered normal. If you were above or outside of, above or below 2 standard deviations away from the mean, you're literally considered not normal. And that not normal phrase comes from the normal distribution. Okay. Anyway, going a little further with this, and not by much because we're going to get right into the calculations. This is the equation for the normal curve, for the Poisson distribution. Okay. Looks pretty complicated. It's got the letter E in it, which means it is partially an exponential function. Okay. These are all constants. Pi, of course, 3.14. Your standard deviation, of course, is going to depend on your data set. And then up here, you've actually got this value here. I don't know if you remember what that is. That's our z-score calculation. The value minus the mean divided by the standard deviation is what we call the z-score. And there's also negative 1/2 in there. So the variable portions are the value that, that defines, the range that you're looking for, the mean, the standard deviation, again, the standard deviation here. And that's what defines the function. But of course, the function does change as x changes. So it is an exponential function. For those of you guys who only took grade 11 math and didn't take advanced functions, E is the base 2.71. Okay, so as a result, then you can kind of think, oh, it's not a 2, it doesn't double, it doesn't triple, it's a little bit more than triples, a little bit less than triples, and a lot more than doubles. Sort of idea for an exponential function. But it would look like this, except it's modified. Okay, it's modified. And then these values can go from negative to positive, right? Because if you're above the mean, if this value is positive, then that negative value is going to make a difference. But what you're going to do is you're going to get a function that kind of takes off like this, and then it comes back down again. And the reason why it comes, oops, I didn't leave myself much room. The reason why it comes back down again is it's negative here, but this value is going to be positive. Okay, so what's going to happen in that scenario is you're going to create this normal curve. Okay, and that's the equation for it. All right, and the z-score, of course, is a key component of that. Okay, but that's a little of the theory behind it. Okay, so let's get into some examples because it's the best way to learn and understand how to use this stuff. Okay, so first things first, we look at this example. As you can remember, for our previous example, we did ranges of values. So even for question 6 from your homework, we were like flies from this many hours to this many hours, right? For the the lifespan of a fly. Or for the example that I used in our notes, it was between certain masses. So first of all, we're talking about height. Height is a continuous variable. Okay, and that's key. All right, so the average height has got a mean of 163, and you have to have these stats. You can't do it if you don't have these stats. You need to know the mean, and you need to know the standard deviation. Okay, so my mean is equal to 163 centimeters. That's the average. Let me read it out. The average height of males at Loyola is 163 centimeters with a standard deviation of 7 centimeters. We know centimeters, of course, height, continuous. If the heights follow a normal distribution, which means that heights are normally distributed for the students in our population, find the probability of males that are. And these are all the characteristics, so A, B, C, D. Okay, and we're going to get used to this normal curve. Okay, so my mu is 163, or my mean is 163. My standard deviation, or sigma, is 7. Okay? Now, I want to know this range. Okay, so find the probability of males that are between 156 and 170. Properly written, of course. Probability 156 is less than or equal to x, which is less than or equal to 170, which means it goes from either to the either. Now, it's less than or equal to because it's saying between 156 and 170. So exactly on 156 would be acceptable. Exactly on 70 would be acceptable. So it's less than or equal to and greater than or equal to in that particular situation. And that's how we write it. You'll get used to that. Look at my perfect examples of my notes and stuff like that. What I want to do is have a visual of this. So this is what they say it's normally distributed. When they say it's normally distributed, you draw yourself your quick normal curve. Okay, you know the mean is 163. Okay, you also know values that are 1 above, 1 below, 2 above, 2 below, 3 above, and 3 below. Okay, so 1 above and 1 below, standard deviation is 7. So 1 above is going to be 170, and then 177, it's 2 above. And then 1 below is going to be 1 156 and 149. Okay, and of course you can go 3 above and below if you want to as well. We'll just leave that as it is because the only values we're really concerned about are 156 and 170. Well, 156 barrier is right here. 170 is right here. And if I go like that, I basically want the probability as the area under this curve. So the probability is the area under that curve. Well, that, remember, is 1 standard deviation above or plus 1 standard deviation. This is 1 standard deviation below. And so this is this. And we know that for plus or minus 1 standard deviation, it's going to be 68.27% or 0.6827 as a probability. Okay. Now we know that area because we know the normal curve. If this is normally distributed, our data is normally distributed, and we know the mean and the standard deviation, we can use the normal curve in order to figure that out. Okay, and we know, of course, this is 1 above 170, this is 1 below 170, so we do know the 68% between those two values. A little bug there. Okay, so that is a situation where I kind of call it an in-betweens. How we can figure out in-betweens. This one's a little bit, the next one's a little bit more elaborate, but hopefully you'd understand that the probability that, I'll just go between in words, 156 and 170 is 0.6827. We usually keep 4 decimal places, or 68.27%. That also tells me that in the population, 68% of the students, roughly, are going to be within that range between 156 and 170. Okay, so if I was to randomly sample a population, it says 68%, but if I sampled 10 boys or males in the school, then probably 7 of those, about on average, would fall within that height range. There may be some taller, maybe some shorter, but there's going to be 7 who should be in that range, and that's what's expected. Okay, so that's how we go about doing that. For 170 meters and shorter, again, we know that it's normally distributed, so we draw our normal curve. 163, 170, 177, 156, and 149. Okay, now the area that we want is 170 or shorter. The way that we write that, of course, is probability x being less than or equal to 170 or shorter, less than or equal to, right? Or shorter. Okay, so when we look at that, again, we want to know the probability for that. And we want to figure out the area under the curve. So we've only got one barrier here, the 170, less than 170. And so we want to know this whole area in here, all the way down to the little tail. Now we run into a bit of a problem, and the problem that we run into is we don't know that. If you go back and you look at the original situation here, we know that between 1 below and 1 above, it's 68%. 2 above and 2 below is 95%, but it doesn't ever go all the way down to the end. So that's a bit of a weird calculation for us to do. So we have to use a little bit of geometry or arithmetic. And this is why I do this and I teach this, because I could just tell you how to do it and then you do it. But I want you to understand the bits and pieces that we get out of this. To do less than, I know that this part here is 68.27 because we just did that between 1 above and 1 below. I know this area is 68.27. All right? Easy. Now, what I also need is I need this little tail over here, but I don't know what that tail is. But what I do know is this. If this is 68%, then I know that this and this is going to be 1 minus 68%. Oops, 0.6827. Okay? Because, of course, I know that the whole distribution adds up to 1. So as a result, if I go 1 minus 0.6827, I'm going to get 0.3, I've done the calculation somewhere else, 173. Okay, so that means that both of these tails are equal to 0.3173. Now, I don't want to know both of them, but I do know a few things. One, well, if 2 of them are this, 1 of them, hopefully, is going to be half of it. Does that make sense? Because you can't just randomly do it? Yes, remember, this is a symmetrical function. That means that this and this, if they're in if they're in the same sort of sides, the same distances from the mean, they will be exactly the same thing because this is symmetrical. So if I go down the center, this part, although I haven't drawn it perfectly, and that part are exactly the same. So if I take that value and I divide it by 2, I get 0.1587. So now I know the probability, or 15.87. Now I know the probability of that tail is 15.87. 15.87. So what's the probability? Well, it's going to be this area or this area, or basically both of them put together. So we add them up and we get 68.27 or 0.6827 plus this little piece, 0.1587. And then when I add them all up, it gets I'm going to cheat here and look at my notes, 0.8414. Okay, and certainly use your calculators when you do that. I'm cheating because I've already done a nice, beautiful layout of the calculation for you. But that's what's involved in figuring out a less than. Okay? Let that sit for a bit. It's a bit messy here. You probably should have the other notes with you as a companion so you can understand this video and look at it nice and beautiful and perfect with the colors and all that sort of stuff. Okay, so make sure you have those notes open as a companion while you're watching this video. Let's do another one. The probability of taller than 177. It's not the best normal curve that I've done in the world. Okay, 163, 170, 177, 156, 149. Okay, now I want to know from 177 upwards. So this is the probability that x is going to be greater than or equal to 177. It actually says taller than 177, so I should go greater than 177. Now you may say to yourself, is there a different calculation for that? There isn't a different calculation, and the reason why there isn't a different calculation is 177 is so small, whether you include it in this one, or sorry, don't include it in this one, and include it in this one, the difference is negligible. And as a result, we can't even know that because that barrier, this dotted line that exists here and here, is so infinitely thin that it actually doesn't occupy any differential area. It will make a difference for our next expectation in section 8.3 on using this for discrete variables, because you can use this for discrete variables too, but you have to adjust it. It will make a difference for that one, but not for this one. So whether it's greater than or less than or equal to or greater than or equal to, it doesn't make that much of a difference for continuous variables. Okay. Anyway, I want to know what this little area is here. And you may say to yourself, well, darn it, I don't know how to do that. Yes, you do. Hopefully you can remember that if this area here, right? If this area here, remember that's plus 2 sigma and that's minus 2 sigma. That's 2 standard deviations above, 2 standard deviations below. That's what these two lines are. Okay, this is equal to 95%. Maybe I should put it somewhere else. This area in here is equal to 95%. Or 0.95, let me get it right, 45. 0.9545. Okay? If that's 0.9545, then I know that this tail and this tail are going to be 1 minus 0.9545. Or 0.0455. Okay, that means that this little tail and this little tail are going to be equal to 0.0455. They're symmetrical, so I take that and I cut it in half, and I get 0.022, well, if I round it, 0.228. Okay, and so that means that the probability of this itsy bitsy tail is going to be 0.0228. Now you may be saying to yourself, this is getting crazy. Okay, this is getting nuts. Stay with me. I'm going to show you an easier way to do this, but you have to understand the geometry before you do anything else. Okay, so going through this, although it's the long way to go there, it's the journey, not the destination, and the journey here is important. Okay, so again, that's how I do it. I figure out what one of those is by figuring out what both of those is. I figure out what both of those is by saying, I know what this is. The tails are 1 minus that. 2 tails are that divided by 2 to get what 1 tail is, and 1 tail is what I'm looking for, or what I'm looking for. Okay, and again, this number, remember, means what is the probability of finding a randomly sampled student that would be taller than 177 centimeters, and that is about 2.28%. Or it tells you that 2.28% of the student population in Loyola is taller than 177 centimeters. Which is not, this isn't right. I'm just making this up. I made up this data. Okay? But the point is you'll have data. You'll have real data. Okay, so shorter than 149 centimeters. Let's try that one. I made this one a little bigger. It's probably a good idea. 163, 170, 177. and then 156, and then 149, and okay, there's my barrier, 149. So I want the probability shorter than. Let's see if you can figure that out. X is, my barrier is 149, shorter than, less than. Is it less than or equal to or less than? Shorter than. It means it doesn't include the 149. So it means anything below 149. So it's a less than 149. Okay. Now let's establish our barriers. You take the 149, you draw your barrier. There it is there. Shorter than means it's down here. And it's its tail. Okay, and again, you run into that problem. You're like, I don't know how to do a tail. It's not between two values that I know. So what I do is I use the geometry. I know because this is boop, boop, two below, and this is boop, boop, 2 above. I know that is 0.9545. That means that this and this is going to be 1 minus 0.9545. Again, because the whole curve is going to be 100% or 1, right, for a probability. So, of course, I figured out what that value is, 0.0455, and then I say, well, that's for 2 tails. I only want 1 tail, so I divide it by 2, because remember, these 2 tails are symmetrical, okay? And I divide it by 2, and I get 0.0228. It's actually exactly the same as this, and the reason why it's the same as this is the top tail, right? That's this. And this is exactly the same on the other side. That's this. But we did another opportunity at calculating, and that's an important idea. So the probability of finding a fairly short male in the Loyola population is about 2.2% or 2.3%. Or that means 2.3% of the students are shorter than 149 centimeters, some of those little guys that you see in the halls. Okay, so that's how we start to use the normal curve when we get used to the geometry. You may say to yourself, this is pretty confusing. I don't know if we can do it this way. I don't know if I can do it this way. That's a different story, okay, because there's an easier way to do this. Okay, and I got to bring about some discrepant events, something that's going to make it difficult for us before you say to yourself, oh, okay, all right, I see how I can do it. And then you'll understand where it all comes from, and you'll get used to drawing the curves, and it's just better for you, trust me. I've taught this like a gajillion times, I don't know, like 25 times. And I taught it a bad way, and then I taught it a good way, and this is the best way that I've taught it, and it's been pretty successful for most students. Okay, so keep it in mind. All right, there's other ways to do it too. All right, shorter than 168. Okay, another example. You're like, oh my God, another example. Trust me, this is going to be a reason for this. Probability that's shorter than 168. Okay. There's my normal curve. I know it's normally distributed. If you don't remember, our mean is 163. Our standard deviation, same things from the previous page. It's our same population, 7. They're both in centimeters. So I put 163 for my mean. And then I go 156, and then I go 149, just like I've been doing all the way along, 170, 177. Now 168 is going to be right here. No, I guess I should put notation. So probably shorter than 168. So I have a barrier at 168. So you put down 168 and you say shorter than. Okay, shorter than means shorter, less than. Is it less than or equal to? Shorter than 168 is just less than 168. Now, as I said, it doesn't make that much of a difference for continuous variables, but it will next time. But it's something that we should get used to. Now, there's 168 right here. That's where 168 is. Okay, notice it's not exactly on 170. It's not exactly on 156, not exactly on 149, not exactly on 177. So I know nothing about this. So if I use the technique that I used, for this page here, okay, for the previous page, I can't do it. Every one of them was exactly on the standard deviation values that we're used to. 170, 170, 156, 149, 177, 149, 177. 168 isn't in any of these, so I don't have any particular values to go by. Don't worry. This brings about a situation where you can't use your previous method of geometry. So what do? It's the 100% go-to method. Okay, and the 100% go-to method is using the normal curve and what are called Z-score tables. Okay? What you don't realize is that what people have done is they've taken this normal curve and they've calculated for every particular value there exists. Now, they can't do for every value that's out there, so they have to do it for a value on the normal curve itself. Remember, the normal curve has a mean of 0 and a standard deviation of 1. So it'll be +1, +2. That would be -1, -2. And so they all correspond to Z-scores. So how do I get this? Because what I want is shorter than. I want this area shorter than, I'm not great at coloring, but shorter than 168. That's what I want. Well, how do I do that? Well, this is how you do it. It's always this way, but it does only give us a particular type of a calculation, so you have to learn about the constraints of the technique as well. So what do? Simple. Okay, to calculate a probability that's not one of the distinct points, a multiple of sigma, away from the mean, we calculate the z-score. Okay, and that's what we do first. We calculate the z-score. So for this example, what we would do is do the z-score. Now, where does everybody go? Well, first of all, we have a mean, 163. We have a standard deviation, 7. We have a minus. Now we have an x. Now what is the x? The x is your barrier, this 168. It's the value that you're specifically interested in. Okay? Once you do that, you do a simple calculation. Okay, 168 minus 163. Watch the signs, S-I-G-N, plus or minus. In this case, it's a positive 5 over 7. Now, positive 5 over 7. Okay, 0.71428, and so on and so on and so on. For our z-score tables, and for most, if not all of your z-score tables, 0.714 and so on, we approximate it to 0.71, and we keep 2 decimal places. I know I've been saying 4 decimal places up to this point, and if you go online and you look at a z-score calculator, there will be ones that will go to infinite number of decimal places. But, and Microsoft Excel will do that too. For our purposes on our z-score tables, we're going to go down to 2 decimal places. It's as good as we can get for now. Okay, and it's just a precision that we have. So we get a z-score of 0.71. Okay? Now, what we do from here is important. Okay? Because really the information that's in here comes from a table that looks like this. Z-score table. Okay? And I've got some written on here for your notes, so don't worry. When you see them in your notes, you'll know the z-score table. You can scroll a couple of notes down the road and you can see these values in there as they've been scanned in. This is a table that I've given you an extra handout for, so print it out, have it handy. Do not go back and forth from the computer. Do not go back and forth from the reference in the textbook. Have one of these out. This is worth the printing. If not, save it on your phone. Open it up. Have it there. Make it expandable, whatever it may be. Okay, you need this table. What you do is you take this number, 0.71, and you look it up on the table. Now, the answer that they give you, if you look at the pictures here and here, the answers that they give you will be the value, that's x, like our 168, and less than. It always gives you less thans. It doesn't give you greater thans. It doesn't give you in-betweens. It only gives you less thans. It always gives you less thans. And the pictures show you that. It's this value and this is the area less than. This value and the area less than. I'll show you how to use the less thans to figure out greater thans or in-betweens and stuff like that. But it also comes with drawing the sketch and understanding what you're looking at. Okay? So anyway, thankfully our example is, what's the probability of shorter than 168? It is a less than. Look, my less than, that kind of looks like this guy. See? But I don't know where this 168 factors into this. It's not going to be in this random sketch that's been drawn here. What we have to do is actually figure out that specific value. That's what we use the z-score for. We take the z-score of 0.71. Okay, and how do we do it? Well, we start with the z-score, and we go all the way down to 0.7. Okay, and remember, I want a z-score of 0.71. Okay, so that's 0.7, and then each one of these goes to 2 decimal places. So there's 0.00, 001, 02, 03, 04, 05, all the way to 09. Every possibility that can exist if we round it to 2 decimal places. So 0.71 is going to be the intersection between these two. So we make these guys follow together, and then we go to 0.7611. That tells you that this area here, this probability, okay, is going to equal to 0.7611. Okay, that's a probability of less than your barrier. Okay, so that's what I do. What I do is I take my score of 178 and I say, well, I don't know what that is for my specific situation. But what I can do is if I figure out the z-score, the probability of x being less than 168 is the same as the probability of having a z-score of 0.71. That's taking my data and turning it into this normal curve. I'm taking my data and turning it into a normal curve. We used to call that normalizing the data, because you take your data that's specific to your situation and you turn it into the normal curve, normalizing the data. Okay? And so what I do is I say, okay, I want a less than, I want a less than, good. If I find that z-score on the z-score table, then my probability that x is less than 168 is going to be equal to whatever this value is, this z-score. Again, positive is going to be important, so make sure you look it up. This is the positive side. Okay, so z is equal to 0.71. Okay, so then I go 0.7611. So a z-score of 0.71, I look it up on my table, and in the center here is 0.7611. So the probability is 76%. And so I get my probability from that. So you take your data, you figure out your z-score. Step number one. Step number two, look up the z-score table number. Okay, so now I know the probability of less than 168 is going to be a z-score of 0.71. Look up what a z-score of 0.71 means, okay? Because it's just a little bit to the right, not a full one to the right. And then what I do is I figure out what that area is. And it'll tell you the entire area. You don't have to figure out tails or anything else like that. The entire area. Okay, so that's that. All right, and so then, therefore, the prob shorter than 168 is 0.7611. Simple. Okay, that's a less than. Now, and you could do this for all the other examples that we've done. Okay, but it's a little bit more complicated. So we're going to start with the easiest. The easiest is to figure out a less than. This is a less than. Boop, done. Less thans are easy. What do? You take your value, you figure out your z-score. Once you figure out your z-score, you check up your z-score in your z-score table, and the probability that it is the probability that it is. Easy. Taller than is a little bit different, but not much more difficult. Taller than. Okay, so again here, we put down 163, and we go taller than 154. Now 154, I don't really care where it is. I don't have to put down 156, 163, 170, 177. I'm not relying on that anymore. I'm relying on this technique. It works 1,000% of the time, providing that it's not too big or too small. Okay, so I'm just going to put down my barrier at 154, and it's taller than 154. So what's the probability that x is taller than 154? I write down my barrier. That's what I'm going to do my z-score for in a second. Okay, taller than 154. Taller means greater than 154. Okay, so now when I do this calculation, okay, I'm going to do a z-score. Let me draw what it looks like. First of all, there's my barrier, 154, and I want taller than. So I'm going to have all this stuff all the way up to the tallest of the tallest of the tall. And that's the probability I want to figure out. So how do I do that? First step, z-score. 154 minus my mean, 163, all over my standard deviation, 7. You have to have this before you can do anything else. You have to have your mean and standard deviation. Here it's given. Now this one's going to be a negative. 154 minus 163 is going to be a negative value. And the negative value is negative 9 over 7. Negative. Make sure you keep the sign in there for those z-scores. Okay. All right. Or negative 0. And we have to turn it into a decimal. Oops, sorry, 0. Negative 1.29. 9 divided by 7. Okay, that's my z-score. Okay, so my z-score is negative 1.29. Now, to figure out what that value means, again, I need the trusty table. If you're doing one of these questions and you're not calculating a z-score, and if you're doing one of these questions and you're not going to this table, you're not doing it right. Okay, you're going to go to it all the time. You're going to get sick of this darn table. But it's also going to be your friend. Okay, it depends on the relationship you have with it. Okay, anyway, so what do? We look here. Okay, probability of z is negative 1.29. So I'm going to look up negative 1.29. Step 1, z-score. That means that my probability of x being greater than 159 is the same thing. Oh, wait a minute. That's the problem here, isn't it? My z-score table gives me less thans. I have a greater than here. How do I do a greater than? Well, if I was to figure out what less than is, I know that the whole thing adds up to 100%. So if this ends up being like 5%, then I know this is going to be 95%. If this ends up being 3%, then I know this is going to be 97%. So what do? To figure out greater thans, you go 1 minus the less than. So what I do is I take my greater than and I turn it into something involving a less than. Do you understand how that works? Again, my barrier is at 154. I want to know greater than. I can't do a greater than with this table. Look at the table. There's less thans and less thans. So I can't do a greater than. But I do know that greater thans are the same thing as 1 minus the less than. Okay? So like I said, if this ends up being 7%, then this is going to be 93. So how do you get 93 from 7%? You go 1 minus 0.03 and you get 0.97. Okay, and that's what we're going for. So a greater than is 1 minus the less than version. Same barrier. See, this is a greater than. See, this is a less than. 1 minus the less than barrier. Okay, which is 1 minus, and then having the z-score. Less thans, you have z-scores that go with them. Greater thans, what you have to do is you have to take your greater than and turn it into a less than. And then you turn it into a z-score. And then you look it up on your trusty table. Z-scores, we never add, we never subtract, we never do anything with. Z-scores, we always have to go to this table to determine what it means. So we figure out a z-score of negative 1.29. Now in this case, I go to the left-hand side. See, this is where all the negatives are. And I go to 1.2. See the green, negative 1.2? And then I go all the way up to the 0.09. That's negative 1.29. And they zip come together at that particular value, 0.0985. 0.0985. Again, I go barrier, z-score, probability. Okay? The only thing that's special in this one is for a less than, it was barrier, z-score, probability. For here, it's greater than, 1 minus the less than, barrier, z-score, and then I get to the probability. Now, it is a little bit of arithmetic here. It's going to be 9015. Did I do that right? 9015, my brain, a little bit of brain fart there. Okay, so this means two things, remember. This means, therefore, the probability of any student being taller than 154 centimeters, pretty darn good, is about 90%, or 0.9015. Or it also means 0.9015 of that frequency of students, or percentage of the students are going to be taller than 154 centimeters. Okay? So again, it's either a probability of any random individual having that characteristic, or it's a percentage of the whole. So if I sampled 10 kids, 9 of them should be taller than 154 centimeters. There'll be only one little guy on average. Okay? So it's a bit tough. Okay? So you got to look at it slowly and carefully. The notes that I have for you are a lot prettier. So have a look at those. Okay? And again, in summary, to start with, we've got a less than, pretty easy, right? Less than, figure out the barrier. Once we figure out the barrier, figure out the z-score. Once we figure out the z-score, then because it's a less than, the z-score we look up the z-score, we get the probability. It's easy. For here, we have a barrier, but it's a greater than. So we take the greater than barrier and we turn it into a less than by going 1 minus it. Use the geometry in our favor of the curve. And then we, of course, go, once we have a less than, okay, barrier, then we have a z-score. Once we have a z-score, then we have a probability, and we've got a bit of arithmetic, and we get to the final answer. Okay, repetition is going to be key with this. The more that you do this, the better. Okay, so let's move on. Here it says, what's the probability that a boy will be 171 centimeters or taller? Same data. Obviously, different questions are going to have different data. My mean is 163. My standard deviation is 7. Always have it somewhere handy. Okay. I always draw a sketch. When my daughters were learning this stuff, they would come to me and say, Dad, can you help me? And if they didn't have a sketch, I would say, go away. Go draw me a sketch and come back, and then we'll talk. Because you need to have a sketch in order to visualize this. I mean, I'm a visual animal, but most people just need to have a sketch so they can see what they're looking for. 171 or taller. So what's that look like? 171 or taller. probability 171 or taller. Oh, that's a greater than or equal to 171 or taller, right? Like 171 or more. Okay, so greater than or equal to. Now it's no different than a greater than. We do exactly the same thing as long as the variable is continuous. So I've got my mean at 163. I go all the way to 171. Again, it doesn't matter where all those values are. I want 171 or taller. Okay, so that's going to be this tail right here. Okay, now remember, we can't calculate 171s or tallers. We can't do or tallers. We can't do greater than. So see, that's a greater than. This sheet does less thans. We need to make it a less than. So how do we make it a less than? Well, to make it a less than, a greater than, this is the same as this minus that little tail. Oh, sorry, this tail is equal to the whole thing minus this particular area. So what I do is I go, okay, if I take the less than 171, that's this thing here, I can figure that out. Probably x is less than 171. And then all I do is I go 1 minus that. Now there's another tricky way to do it, but I'm not going to get you to the tricky way because that messes people up. But you may see it in some videos and stuff. I recommend this until you're ready for it. I can do it because it's no problem. But for you, until you're familiar with it, I wouldn't. So for a greater than, it's 1 minus the less than version. That's what you basically want to take as a formula. So a greater than or greater than or equal to is 1 minus a less than or equal to or less than. Okay, that's basically the idea. Okay, and that's how you can do it. And it works out perfectly 100% of the time. Okay, now, I can't do 171. I can't look up 171 on here, remember, because what I have to do is I have to figure out a z-score for the barrier. So first step, z-score. 171 minus my mean, all over my standard deviation, and you have to have that information. Okay, this is going to be a positive 8 over 7. Let me just get my good copy calculations because I'm going to be lazy. I guess I could do it here if I want to. 8 divided by 7 equals 1.14. Positive 1.14. That means, because it's a less than, it's the same thing as the z-score. My z-score is positive 1.14. Then what do I do with my z-score of 1.14? Trusty table. You go to 1. This is the positive side. So 1. Oh, I've got 1.1. 1.14. 0.8729. And so it's going to be 0.8729. So for greater thans, remember it's 1 minus the less than version, same barrier. And then 1 minus the z-score. You go from this to the z-score. And then with the z-score, you go to the table, and then you do a bit of arithmetic. And that's going to be 0.1271. So therefore, 0.1271 is prob of taller than 170. Oops, 171 centimeters. Okay? Or 12%, almost 13% of the students are going to be taller than 171 centimeters. Okay? Next example, what's the probability of boy will be 161 or taller? It's probably getting kind of repetitious, kind of boring, but this is a good way to sort of test things. If you want to test yourself and do it yourself, press pause on the video, okay, or stay away from your notes. Give it a try now yourself. That's the only way for you to know really how to do it. 163. Okay, so we put our barrier in, 161. Okay, I know that's going to be the probability that x is going to be 161 or taller. Put down my barrier. Taller means greater than 161 or greater than or equal to. To do a greater than, what do I do? Right, 1 minus the less than version. What do I do after that? Well, we can't look up 161 on our z-score table. And if you're not looking up probabilities in the z-score table, you're doing it wrong. Oh, wait, I need a z-score. Because, of course, the probability that x is less than is also equal to a z-score. A less than or equal to is always equal to a z-score. So I got to figure out what that z-score is. 161 minus 163 all over 7. That's going to be negative 2 over 7 or negative 0.2 divided by 7 equals 285, so 29, 0.29. And again, you do your best with your rounding. It is what it is. Okay, nothing too crazy. All right, and so again, Greater thans I can't do. I can do 1 minus. Less thans I can do. Less thans are the same thing as a z-score of negative 0.29. 1 minus, and now to get this number, I got to go to the z-score table. Negative 0.29. I don't have it on here, so you got to check it out. It's negative 0.29, negative 9, 0, negative 0.29, 0.3859. You have to look that up on your own. Kind of scrunched in on my room here, right? Got in the way. Okay. We do that quick arithmetic. It's going to be 0.5141 if I did that right in my, oops, 6141. See, there you go. Good thing I checked my answer key. 0.6141. So therefore, the probability of a student being greater than 161, 161 centimeters tall is about 61%. Or 61% of the population is that tall. So if I sample 10 of them and it was a random sampling, then I should get 6 of them being taller than 161 centimeters. Now what we haven't done yet is, oops, I forgot to draw this. Bad, Mr. Henry. What I haven't done yet is a betweensies, or an in-between. And this one's a little tough. Okay, the arithmetic makes sense, but getting used to doing it, okay, we got one for greater thans, that's no big deal. Now we have to do an in-between. This is something that's between specific values, and this is actually very commonly done. So it's a very important calculation to be able to do. So we got our mean 163, still the standard deviation of 7. I want to know what's the probability of being between 161 and 171. Okay, so this is the probability that x is between 161 and 171. And that's really how we write it using domain notation, right? Okay, x is between, see it's literally between 161 and 171. It's going to be greater than, if I look at it this way, than 161, and less than 171. Okay? Now, how do I do an in-between? Well, there's a lot to this. Okay? How do I do an in-between? It's a little bit weird, so I'm going to do a little sketch over here. So how do you do an in-between? Well, what you do is I can figure out from 171 down. That looks like this. So the probability of, let me draw a little sketch here. Probability of this, okay, in between these two values here, is going to equal, well, what I can do is I can do 171 or less. 171 or less is this value right here. Okay, it's too much, obviously, for my calculation, because the area under the curve not only does it encompass this sort of center section that I have here, like it should sort of cut off right here, but it's got this extra tail on here. So what do I have to do? I want to subtract the tail. Now it just so happens that the tail that I want to take off so I can get, have this area blank and this area blank and just have the area in between, okay, is actually the second barrier. So if this is 171, and this is 171 and 161, okay, this is going to be 161. Now remember, I have to put it in terms of less thans. If I don't put it in terms of less thans, it's not going to work. So for me to get an in-between, what I do is I take 171 or less and subtract 161 or less. When I subtract those two, what am I going to get? I'm going to get an in-between. Okay, because what I'm going to be doing by subtracting is I'm going to be erasing that. And then of course you can see that it looks like that one, except a pretty ugly version. Okay, or you can just memorize it. Okay, the way that it works is you take the probability of x being less than or equal to the big barrier, that's the biggest barrier, the biggest value, minus the probability of x being less than or equal to the small barrier, So you have the whole thing and you subtract the little thing. Okay, and the difference between those two is going to be the probability that you're looking for. Okay. Now, I've taken a less than and a greater than and a real weird one, and I've turned it into a less than minus a less than. Okay, so again, an in-betweens is a less than, big barrier, minus a less than, small barrier. Okay, my two barriers are here and here. I got to figure out a z-score for this barrier. Okay, which is, we've already done it up here, negative 0.29. And then I've got to figure out a z-score for this barrier. You've got two barriers. Each barrier, you have to do a z-score for each barrier. Okay, and this is going to be 171 minus 163 all over 7, which is again my same positive 8 over 7 or 1.14. I'm doing this just for the sake and ease of calculation so you can understand how to do less thans, which you've already done, greater thans, which we've done a couple of, and now an in-betweens. Okay? So we get the two z-score values. So remember, the probability of x being less than 171 is the same thing as the z-score that goes to it. And that's 1.14 positive. And then for the probability of less than being 161, that's going to be this z-score. Negative 0.2, oops, sorry, z equals negative 0.29. Again, I have nice, beautiful calculations that don't look so ugly. Oh gosh, that don't look so ugly for you. Okay, and then we can go ahead and do those calculations. I could a bit of run in a room, or didn't really space it out very nicely. But either way, I go up on my z-score table and I look up 1.14. Okay, so 1.14 and a 0.8729. And then I look up negative 0.29, negative 0.29, all the way across, 0.3859. Okay, and then I subtract those values. Okay, and when I subtract those values, I'm not going to use my calculator to do that. I'm going to use my cheat sheet, 0.4870. Okay, now a couple of clues when you're doing an in-betweens if you don't have it down pat. Okay, so a greater than is equal to 1 minus the less than version. Okay, a between is equal to probability that x is less than the big minus the probability that x is less than a small. And you've got lots of examples to practice in your notes and stuff like that. Okay, if that's the case, then less than big and less than small, and so you'll get the particular value for that one for in-betweens. And I have a nice, beautiful version of that. I even have a little sketch that looks a little bit better than this, and so on. Okay, so the probability of getting between 161 and 171 is going to be 0.4870, or about 49% likely, which means if we were to randomly sample the population, roughly 5 of 10 of those kids would be, or those males would be between 161 and 171 centimeters tall. Okay, now you got to get comfy with this. Look over the notes, try the examples yourself in the blank notes. It's a really good idea, and then get into this. The nice thing is questions 1 and 2 are pretty easy. And they start off with just the mechanics of this, and then they actually get to questions. But remember, look for the mean, look for the standard deviation, and go for it. 12 and 13, kind of difficult. I don't expect you to get those. Okay, so I'm expecting people to ask me how to do those ones. They're a bit tough. If you can do 1 to 8, you're in great shape. Okay, thanks for that. Talk to you later.